WaterIoT is a complete smart field watering system. It acts by processing external environmental conditions, both by accumulating in-field data and by using weather predictions. The key aspect of the system is the high customizability, offered by already built-in solutions like a Telegram bot, which offers an entire overview of the system status and to configure various aspects of the system, or via ready-to-go REST APIs to give the user the option to implement its own solution and automatizations. WaterIoT is developed according to the microservices architecture. More than 10 services have been developed for the basic functionalities of WaterIoT. This kind of development is possible thanks to Docker containers. Each service is in a self-contained container, and this allows an easy development and, most important, an easy deploy in a cloud environment. It's easy scalable and easily extensible thanks to the REST APIs and a well-structured code base that follows the object-oriented paradigm. It is at runtime configurable. The most important configurations are managed by a single service, while all other services require or modify their settings directly from it. The system is hot swappable. Thanks to the microservice architecture, the system doesn't require to be shut down before connecting or disconnecting a new physical device. Moreover, each device has its own static ID, so it can be individually recognized within the system itself. Furthermore, each device can have a man-to-man relationship with each other. This means that one or more sensor devices implemented by the Raspberry DevCon service can be connected to one or more actuator device implemented by the Arduino DevCon service. This at-runtime configurable connection via the device config allows the user to create a group of devices that is helpful when the watering control needs to decide on which actuator to actuate. Not all the services are connected to each other. There is a layered architecture in those connections, starting from the service and device catalog, that is the lower one where all old services base their functionalities. On top of that, the device config and the watering database are the two storage-like services. Going forward, the two device connector and the two adapters are listed, and finally the water control that uses all the bottom services to work. In the sideways, we find three services in particular that are not directly used to implement the watering logic, but are used mainly to monitor as a dashboard or to configure in an easy way the system. This is the overview of the most important services in terms of watering logic. The logic starts its work from a Raspberry DevCon. It communicates with the service and device catalog to inform that it is alive and to ask information from other services connected to the service and device catalog itself. Uses the device config both via REST to get information immediately or asynchronously via MQTT. Publishes the sensor readings via MQTT to the ThinkSpeak adapter and to the watering control. Finally, the Telegram adapter can require the readings from the Raspberry DevCon via REST. In conclusion, the Raspberry DevCon offers both REST and MQTT endpoints for injecting within the system the readings from the sensors. Those sensors measure the air temperature and humidity and the soil humidity. It periodically publishes on MQTT, and the period of publish is stored in the device config. The Telegram adapter uses only REST endpoints and connects almost to all the services to retrieve information about their status or to change some parameters, like in the device config. The Telegram adapter is an adapter-like service. It is between the system and the external Telegram APIs, and it offers to the user a fluid direction thanks to inline keyboards, a complete system configuration, and a complete system overview, like the watering algorithm state, server resource utilizations, and a real-time retrieval from the sensors. The top-level service, the watering control, uses all the services to configure itself and to execute the watering algorithm, named as Drupal. The watering control is the main service in WaterIoT. The main goal is to convert LS data using the ones received via MQTT and the ones stored in ThinkSpeak, with the thresholds set in the device config. A database of user-configurable thresholds is available via the watering database. The Telegram bot offers options to create or delete this default configuration, or to apply them to the device config. The decision is took based on an accumulation of those data and the next hour's weather forecast. The weather forecast is get using the OpenWeather adapter. Finally, it decides to turn on or off the irrigator, based on the Raspberry icon that required the execution of the algorithm. Based on its ID, the group is retrieved, and the irrigator within it are turned on or off.
As you can see here, with the command nano docker compose, we can explore all the services we have in our system, such as the catalog, the Telegram adapter, etc. And each of them is assigned to a specific port with some specific parameters. Then we need to load the environment with the command source load env.sh, and by doing make we can start building the project. When the make command has finished, to check if all the containers are healthy, you can simply run the command docker compose ps. As you can see, you will get a sort of a dashboard showing all containers and their state. To check the logs of a specific container, just run the command docker compose logs -f telegram adapter, or the name of your container. The -f option allows to follow the logs while they are created. In order to simplify the user control over the system, we decided to implement a visual dashboard. This is available at port 9000, and as you can see, there is a list of all containers and their state. If it is green, they are running properly, otherwise there is a problem. Another dashboard is available at port 1881. This shows all the sensors and their values, such as the soil humidity, their temperature and their humidity. In addition to that, there is also a little image that shows the weather of the position where the system is. The system has been designed to be as scalable as possible, and in fact, as you can see, there is the possibility to choose more sensors. A key part of the project is the interaction between the user and the system. This is achieved thanks to a Telegram bot with many commands. The first thing to do is always to authenticate. With the command /readings, you can see all the values of all sensors. If you have multiple devices, you can choose which device you want to show. With the command getRT and the number of the device, you can see the value of the temperature. The same can be done with the command getRU and getSoilU. The command /pos allows you to select a specific location. You can use the integrated location selection given by Telegram, or you can set the position by using the command /pos and passing as arguments the latitude and the longitude. With the command /database, you can see some presets for the thresholds of the sensors. These values can be set by the user. You can add or delete a database. These values will be used by the watering control to decide which action needs to be executed. If you have multiple devices, with the command /links, you can edit your links in order to achieve the perfect setup.